You're told never to try at home. Today we're experimenting with water and high voltage electricity. Now we're told all the time never to get electricity even close to water. But why? What exactly would happen if we accidentally dipped electrical cables into a glass of water? The purpose of this video today is to find out. Now for our first experiment, I rigged up this very unsafe device, which basically takes the electrical power out of my house and splits it into these two wires. If I touch these two wires together now, you can see the light flickers behind me. When they're disconnected, the light is off, but if the wires touch, the light turns back on. Now for this first test, I filled up this glass with distilled water. Now distilled water has nothing in it. It should be pure and non-conductive, meaning electricity should not be able to flow through it. Let's see if that's really the case. Here we go. Absolutely nothing. So you can see that both wires are completely submerged in the water here and nothing is happening to the light. It's not even flickering. But let's try touching the wires underneath the water and see what happens. Wow, we made this little pop and I saw a little flash of electricity and the light turned on behind me. It's actually pretty cool. And I can see little bubbles coming off the electrodes. Makes me wonder if those are little hydrogen bubbles. Maybe we got a little mini electrolysis generator here. So update guys, we have confirmed that distilled water is non-conductive. We had absolutely no reaction. So I've gone ahead and filled our glass up with tap water now to see if there's any difference. Electricity versus tap water. Here we go. Oh, interesting. Look at that. It looks like the light is actually turning on a little bit. It's not like brightening right up, but there definitely is some electrical flow. If I pull the wires further apart, it gets dimmer. And if I bring them closer together, it gets a little bit brighter. That is interesting. Look at that. If I move the wires, the light kind of flickers. And these wires aren't touching, they're just submerged in the water itself. So apparently tap water is slightly conductive. I mean, it won't run the full current through it, but you can see there definitely is some kind of electrical connection because these wires are not touching. And of course, if we touch the wires together, then it goes to full bright. That's amazing. So obviously we're not getting the full current flow through the water, but we are getting something. That's very interesting. Now, I think the original concerns of electricity mixing with water stem back to when people had portable heaters falling into their bathtub or dropping their hairdryer into the bathtub. We have to remember that bathtubs are not just tap water. They have soaps and shampoos in them. So for this next experiment, let's try mixing in a little bath soap to the water and seeing how that changes things up. Make it a little bathtub martini. It's not dirty yet, it will be. Voila. Okay, our wires are live. Here we go. See, things are a little bit brighter. Oh yeah, that light is quite a bit brighter. I wouldn't say it's full bright, those are wires touching and that's disconnected. I'd say we're maybe 50 to 75% of the power, but that's quite enough. That's enough to give you a tingle if you're sitting in a bathtub with a high current device like a hairdryer. So yeah, bath soap and water definitely increases the conductivity. Interesting. So that was pretty cool. We saw exactly what house power does in soapy water. So I think it's time to level it up now to high voltage. Now you guys remember this thing. This is a big old bulky neon sign transformer. It pumps out 12,000 volts of electricity, but it's current limited to 30 milliamps. These are the kind of things that used to power those big neon signs that you see around the city. Now in contrast, if you ever get out to a fast food restaurant or any kind of business for that matter, you'll probably see a neon sign like this. These are still powered by a neon sign transformer, but because of newer technology, they can deliver the same power at a fraction of the weight. Now I want to give a shout out to my friend Jerem. He's the one that gave me this neon sign. Unfortunately, it's broken, and so there's probably not much use for it, except for the power pack on the back. Now to salvage a precious power pack like this, all we have to do is disconnect it from the sign, clip the wires as far up as we can go, and then strip the cable back to expose the small wire inside. Now the voltage we were using out of our house power was 120 volts. In contrast, these are 10 to 12,000 volts, exponentially higher. And that's why high voltage signs have such a thick casing of rubber around them. So for this last experiment today, I want to demonstrate the power of high voltage electricity. I've cleaned and dried this glass completely because we're going to go back to using distilled water, which theoretically is non-conductive, right? So how will high voltage electricity work with distilled water? We're about to find out. Now there are a couple of really important things to understand about high voltage electricity. Number one, it's so powerful it can actually jump through the air. A normal electric circuit, you have to touch the wires together, but not with high voltage. High voltage can jump the gap and form its own electrical bridge. Which means flimsy little gloves like this aren't going to save you. So even if you're wearing gloves, high voltage electricity can still surge through your body. Now luckily 30 milliamps isn't enough to stop your heart, theoretically. But we never really want to take that chance. So whenever you're dealing with high voltage electricity, a good rule of thumb is to put one hand behind your back and operate everything else with the other hand. We want to avoid the electricity crossing through our heart as much as possible. High voltage electricity versus distilled water. Let's power it up and see what happens. I'm actually going to put the tip of this one down into the water first, and then we'll try the second one and see what happens. Oh, look at that! Not only does distilled water conduct electricity, but the electricity actually jumps to the water before it even makes contact. Look at this. When I start bringing this second one down, you'll start hearing it buzzing. And if I go a little bit further, it's like little purple lightning bolts jumping down to the water. That's so cool! If we go right into the water, it completely disappears, but I can still feel this thing buzzing. Bring it out slowly. Oh wow, did you see the water get stuck to that? That is bizarre. That is really cool. I was not expecting that. So this isn't something I was expecting to see, but as I start pulling the electrodes out of the water, it seems like the water connects to the electricity. At least it gets about 3/4 of an inch off the surface and then drops back down to the dish. Look at this, I can do both at once. That is crazy. It feels like I'm pulling the surface of the water up. Wild. What happens if I bring them closer together? Wow. So apparently the water is even more conductive than the air, because if I hold the two together close to the surface of the water, it will choose to go through the water rather than through the air. That's very interesting. And these little water bridges that we're making are nuts. It doesn't seem to matter where I place the electrode in the dish, the electrical pattern doesn't change much. Like I can bring them far apart, close together, it's exactly the same. See like tinges of green in there.